Hello, so in today's video we're going to be discussing derivatives of logarithmic functions. So first we're going to discuss a few of their properties and then later on get into a few examples. So first we know a logarithmic function with a natural log is written by y equals ln of x. And this is differentiable because the inverse is differentiable. So this is differentiable because we know its inverse is y equals e to the x is the inverse, which is differentiable. Alright, so that's a pretty straightforward definition. And we know that this should be a review of Calc 1, d dx of ln of x equals 1 over x. So for a general derivative, say f prime of x, we want to find the derivative of b to the x here. So f prime of x equals d dx of b to the x. And so to differentiate this, we first need to rewrite it in the form d dx of e to the x ln of b, where we have all that in the exponent. And now this turns into a type of chain rule problem. So this is going to equal e to the x ln of b times d dx of x ln of b. Remember, this is chain rule, review Calc 1. So this we can rewrite as e to the x ln of b. So everything here is preserved by the chain rule, and then we just need to take the derivative of that, which is just ln of b. And I'm not going to show all those steps because that should be reviewed for you. As such, we can combine this because after we do the multiplication, leaving us with e to the x ln of b, because remember the e and the ln cancel each other out. So therefore, d dx of b to the x equals b to the x ln of b. So we're going from here to this here. So that's how we find like a general derivative of these types of problems. Now we also need to take note of a few different cases that we might have, because that's going to drastically impact the way in which we solve these problems. So different cases of derivatives. So first, you can have a case where you have a constant base, so just any number, constant base, and constant exponent. And that would have you d dx of b to the a, where b and a are both constants. Second possibility, you could have a variable base and a constant exponent. So that would give us d dx of f of x to the n, which you could rewrite as n times f of x to the power n minus 1 times f prime of x. So similar to the chain rule. And then 3 constant base and a variable exponent. So then you'd have d dx of b to the g of x equals ln of b times b to the g of x times g prime of x. Again, another variation of the chain rule. And then the fourth possibility we would have is a variable base and a variable exponent, which would give us d dx of f of x to the g of x power, and then this is where we need logarithmic differentiation, which we went over before. So that's some of the different cases we need to discuss. Okay, so now we're going to take a look at a few examples. And the first one is just going to be differentiate. And then our problem is f of t equals 3 to the power cos of 2t. So now we want to find f prime of t. Well, this is similar to what we looked at here in case 3, where we have a constant base and a variable exponent. See, we have 3 as the constant, and then that's a variable up in the exponent. So therefore, we're going to follow this setup to evaluate the derivative here. So f prime of t equals ln of 3, ln of b, just as shown in the case. So ln of 3 times 3 cos of 2t, and then times the derivative of that, so times d dt of cos of 2t. So really the only thing you're taking the derivative of, like in a raw derivative sense in this problem, is cos of 2t. This is mainly just plugging in different parts to that formula we saw. So we know derivative of cos of 2t is going to be negative 2 sine of 2t. That should be a review from Calc 1, so I'm not going to go over how to do that. So f prime of t equals ln of 3 times 3 to the cos of 2t times negative 2 sine of 2t. And then that's our final answer for this one. So again, just looking at those cases we discussed earlier. Now we'll look at different example. Call that number 1. This one here will be number 2, where we have y equals x to the 1 over x. So that's going to be variable base and variable exponent, so like case 4. So that's where we're going to have to apply the logarithmic differentiation to both sides. So y equals x to the 1 over x, so we want to apply ln to both sides. And that gives us ln of y equals ln of x to the 1 over x. And then that simplifies down to ln of y equals 1 over x, because remember what ln allows us to do, it allows us to pull that exponent and put it down at the side. So 1 over x, ln of x. That's what we're left with. And now from this step we get ln of y equals x to the negative 1, because we want to get that x up top. So we just bring x up, get rid of that fraction there, x to the negative 1, ln of x. Now we just need to differentiate both sides. So applying d dx to both sides gives us d dx ln of y equals d dx of x to the negative 1 ln of x. So taking the derivatives of both sides just gives us 1 over y dy dx equals negative x to the negative 2 ln of x plus 1 over x to the negative 1. And remember, this here is just the product rule from Calc 1. So everything in this right-hand term here is coming right from there, and that's just a product rule problem. That's why we wanted that exponent to be negative 1, because it makes it much easier in dealing with that fraction. At this point, now we just need to get dy dx by itself on one side. So doing that, we have dy dx equals, we're moving the 1 over y term over to the other side, so times 1 over x squared minus ln of x over x squared. And then we'll keep that y term on the outside. So we have the y factored out there on the side, but remember from the original part of the problem, if y equals x to the power 1 over x, so we can rewrite that in its most simplified form, where dy dx equals 1 over x squared minus ln of x over x squared times, and then we know y equals x to 1 over x, so times x to the 1 over x. And that has everything with x variables on the right side. And make it look a little bit more like an equal sign, and we're done with this problem. For the next set of problems, we're going to differentiate. We have log base 10 that we're going to be dealing with. So this number 4, same instructions, we're just differentiating. This time we have f of x equals log base 10 of 2 plus sine of x. Well, we know f prime of x equals d dx of that whole term there. So d dx of log base 10 of 2 plus sine of x. So now we have to take the derivative of this, and this breaks down into two different parts, which is 1 over ln of 10 times 2 over times 1 over 2 plus sine of x times d dx of 2 plus sine x. And now we're just combining these cases. So we know the derivative of 2 plus sine x is just cos x. That's going to be on the top, so cos of x. And then on the bottom, we just combine these two terms together such that ln of 10 times 2 plus sine of x composes our denominator. And therefore, that's the derivative for this problem. Next, we're going to look at problem 5, which is going to be g of r. So again, this can be any type of function, equals log base 10 of square root of r. So we know that g prime of r, which is what we're looking for, is the derivative of log base 10 square root r. Okay. So again, by the way we broke it down in the previous problem, we can rewrite that as 1 over ln of 10 times 1 over root r times d dr of root r. Well, d dr of root r is 1/2 r to the negative 1/2. That's just simple derivative, because r square root is just r to the 1/2, so it's 1/2 r to the negative 1/2. And that's going to become our numerator. So 1/2 r to the negative 1/2 divided by ln of 10 times root r. Again, all that's just getting squished together there on the bottom. And you could leave it like this. This would be a perfectly acceptable answer, or you could simplify it down slightly, such that 1 over 2 ln of 10 r is your final answer. Either way, it doesn't matter. You could stop here or simplify it down slightly to that. And that will be our final answer. Now we're just going to take a look at a few integration examples before we wrap things up. So, integration, and then we just have to evaluate. So we have first integration problem here is x to the fifth plus 5 to the x dx. Well, we know x to the fifth, that's pretty easy to evaluate. That's just going to be 1/6 x to the sixth. And then 5 power x, that's going to evaluate to 1 over ln of 5 times 5 to the x plus c. And that's by the formula. I'll just write out the formula right here. That's d dx of 1 over ln of b times b to the x equals b to the x. So the integral of b to the x dx equals 1 over ln of b times b to the x plus c. So that's just the general formula for these types of problems. And that's how we're getting our answer. Here, specifically, how we're evaluating the integral of 5 to the power of x. Now the second example we'll look at is going to be integral of x times 2 to the x squared dx. Now if you notice, the best technique for integration here is going to be the u substitution, so we'll let u equal x squared, such that du equals 2x dx, and then 1/2 du equals x dx. So now we can rewrite the whole integral as 1/2 integral 2 du, or 2 to the u du. And now 2 to the u, that's just going to be relying on our formula we discussed up here, these properties again, specifically right here. So b to the x, now it's just 2 to the u equals 1 over ln of 2 times 2 to the u. So we'll write that right down here. So we have 1/2 times 1 over ln of 2 times 2 to the u plus c. And then we can simplify this down, shove all that on top of the numerator and combine the terms of the denominator, such that 2 to the u equals 2 ln of 2 plus c, and then we know u equals x squared, so we have 2 to the x squared over 2 ln of 2 plus c, and that's our final answer. So for this one, we're just relying on the formula written above, and then that small u substitution. And the last problem we're going to take a look at is number 3, and that's going to be the integral of 2 to the x over 2 to the x plus 1 dx. So here we're going to let u equal 2 to the x plus 1. Now du is just going to equal 2 to the x ln of 2 dx, such that 1 over ln of 2 du equals 2 to the x dx. So we just move that over to simplify things. Now that we have our u substitution out of the way, we'll write 1 over ln of 2 integral of 1 over u du. Now this is a pretty straightforward problem. So 1 over u, that evaluates to ln absolute value of u. That should be a Calc 1 property that you remember, ln of 2 times ln absolute value of u plus c. So plug in our u value here. So ln of 2 to the x plus 1, and that absolute value over ln of 2 plus c, and that'll be our final answer. So for this one, we relied on what the derivative of 1 over u is. That's just ln of u, but you have to put the absolute value on there. And then we relied on the u substitution, where we had to do a little bit of manipulation to get the in the form we liked. But if we see here, 2 to the x dx, that's this term right here, so that's really what we're trying to cancel out as much as possible. So that's the idea of the u sub. u equals that, so we get rid of that. Now we're just left with 2 to the x dx. So how do we manipulate the derivative here? To get 2 to the x dx, we just divide by ln of 2, such that this is our result. And then integrating that just gives us this here, and that'll be our final answer. And that concludes our topic for today.